All right, worksheet 11, we're going to go about solving trigonometric equations. So this will be somewhat similar to the inverse trig that we've been doing on worksheet 10. In fact, it's going to involve some amount of inverse trigonometry, but we're also going to be looking just at solutions that are on the unit circle, at least to start. So in these first 8 problems, we're going to be finding 4 solutions that are between 0 and 2 pi, that being just within the unit circle, which is going to answer sort of the other question that kind of comes up when we're doing inverse trig of if, take this first example, cosine of theta is equal to the square root of 3 over 2, then what is theta equal to? If we're only using inverse trig, where we say that theta is equal to the cosine inverse of root 3 over 2, we're only going to come up with the angle pi over 6, because inverse cosine is defined only in that first and second quadrant. However, if we start from a more general statement of cosine theta is equal to square root 3 over 2, what is theta equal to? Well, now we're opening up several other possibilities. In fact, if we don't restrict ourselves to just the unit circle, there are an infinite number of solutions. So we're going to start by saying, okay, let's only look at the unit circle and find all solutions that are between 0 and 2 pi. And turns out if we do that, we're taking cosine of theta is equal to the square root of 3 over 2. Cosine of theta is equal to some positive number, so I should be looking for angles in the first and the fourth quadrants. And I end up with the angles pi over 6 and 11 pi over 6. So within the unit circle, I have those 2 angles that solve this equation. All right, let's take a look at question 2. So now I'm starting with the square root of 3 times tangent theta plus 19 is equal to 18. And again, we're going to solve for theta. So step 1, I'm going to subtract 19 from both sides, which is why I end up with that -1 on the right, then divide by square root of 3 to get the tangent theta is equal to -1 over square root of 3. And then I'm multiplying by that root 3 over 3 in order to rationalize the denominator, which gives me the familiar value of -root 3 over 3. Now I know that -root 3 over 3 happens at pi over 6. So now I want to find all of the angles within the unit circle where tangent fits that pi over 6 reference angle, but is negative. I know that tangent is negative in quadrants 2 and 4, so I want the pi over 6 angles that are in quadrants 2 and quadrants 4, which works out to 5 pi over 6 if we're in the second quadrant, and 11 pi over 6 if we're in the fourth quadrant. Right. In problem 3, we're starting from 2 sine squared minus 1 equals 0. So we'll try to isolate sine theta, which means first we add 1 to the other side, then we divide by 2, and get that sine squared is 1/2. But be careful not to stop here, because even though sine of theta equals 1/2 does come out to a solution, this is sine squared equals 1/2. So we're going to need to take a square root first. If we do that, because we're taking the square root of a variable, we end up with a plus or minus on that square root of 1/2, because sine of theta itself could be positive or negative, because regardless of if sine is positive or negative, if it gets squared, it comes out to positive. So we get that plus or minus on that square root of 1/2, and then if we rationalize 1 over square root 2, we're going to get square root of 2 over 2, which is that familiar value from the unit circle. Now, if I take the positive square root of 2 over 2, I get that sine is in quadrants 1 or quadrant 2, sine of theta, theta being that angle that's in quadrant 1 or quadrant 2. And if I look at the negative value, that means that sine of theta, or rather that theta, is in quadrant 3 or 4. Meaning that I'm actually going to get 4 solutions to this one trig equation within the unit circle, because there is a solution in every quadrant, because it doesn't matter if sine itself is positive or negative. And we're looking at all of those angles that have pi over 4 as a reference angle. So theta is pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. Any one of those 4 angles will solve that original equation. All right, in problem 4, I again have a sine squared function. So I have 2 sine squared plus sine of theta is equal to 0. So my first step is going to be to factor sine theta out of every term. So if I pull that sine theta out, I'm left with 2 sine theta to the 1 power, which so I have to note it with the 1 there to signify that a sine has been divided out of that term. And if I factor sine theta out of sine theta, all I'm left with is 1. So 2 sine theta plus 1 multiplied by that sine theta. Now, going back to algebra, I have the zero product principle that says if I multiply 2 things together and I get 0, then one of those 2 factors must be 0. So I can split that up into 2 separate equations. Either sine of theta is equal to 0, or 2 sine theta plus 1 is equal to 0. Let's start by just solving out the one on the left. Sine of theta equals 0. That has 2 solutions on the unit circle. Theta is either 0 or pi. And if you look back to the way that all of these questions were phrased, we wanted solutions that were between 0 and 2 pi, but we had a bracket on 0 and a parenthesis on 2 pi, meaning that I'm including 0 in my set of solutions, but not including 2 pi in my set of solutions, which is why I'm going to take 0 instead of 2 pi, even though both would be that positive x-axis angle. So just by definition, I'm going to take 0 as the solution. Solving the other side, I had 2 sine theta plus 1 is 0, which means sine of theta must be equal to -1/2, which puts me either in quadrant 3 or 4. So I'll get a couple of solutions here. These are angles that have a reference angle of pi over 6. So this will be 7 pi over 6 or 11 pi over 6. So now I need to put all my solutions together. So theta could be 0, pi, 7 pi over 6, or 11 pi over 6. And all 4 would solve my original equation. Any of those 4 would solve my original equation, I should say. All right, problem 5 has a bit of a trick to it. It starts out as 2 sine squared of theta plus 3 times 1 plus cosine theta. Let me try that again. 2 sine squared theta is equal to 3 times 1 plus cosine theta. There's the right inflection. So I have a mix of trig functions here, which makes things complicated. Usually it's helpful if I'm trying to solve an equation like this, if I only have one trig function. I can deal with it showing up multiple times, but if I have different trig functions that show up, then I can't just immediately factor it out of one of those functions out of every term. I'm going to need to do some exchanging using one of the trig identities that we used back in worksheet 5. So in this case, since I have sine squared and cosine theta, I'm going to want to change my sine squared over to be a cosine squared function. Because using a Pythagorean identity is relatively easy. whereas trying to change just a simple cosine theta to be a sine theta is going to be significantly more difficult. So since sine is the squared function and cosine is not squared, I'm going to change my sine squared to 1 minus cosine squared of theta using that Pythagorean identity. So that's that piece that's there in blue. It's just changing sine squared to 1 minus cosine squared. And then I'm going to go about solving this equation, trying to isolate cosine theta. So my next step is to distribute the 2 on the left and the 3 on the right. Then I'm going to move everything over to the right side of the equation and combine like terms where possible. Add 2 cosine squared over, subtract 2 to the other side. So I end up with 3 minus 2 is 1, which is why that 1 is highlighted in blue in the third line. So 2 cosine squared plus 3 cosine plus 1. Now, that third line is a quadratic equation that can be factored. If factoring with trigonometric equations is daunting, then see the part in purple in the upper right part of the screen, where I've simply changed cosine theta to x. So it looks more like a traditional quadratic equation from algebra. So if I'm factoring 2x squared plus 3x plus 1, that will factor to 2x plus 1 times x plus 1. And then simply replace x with cosine theta to get the factored version back here in line 4, which should be 2 cosine theta plus 1 times cosine theta plus 1. And now that that's been factored, I should be able to split up those two factors and set each one equal to 0 independently, because again, using that zero product principle, if I have 2 factors that multiply together to get 0, and specifically 0, then I can split up those factors and set each one equal to 0. So on the left, I've got 2 cosine theta plus 1 is equal to 0, and cosine theta then is equal to negative 1/2. And on the right, I end up getting that cosine theta is equal to negative 1. So if I want to put all my solutions together, from the left side, I know that cosine is negative, so I'm going to be looking in quadrants 2 and 3, and I'm going to need the angles that have a reference angle of pi over 3. So that's going to be 2 pi over 3 and 4 pi over 3. Those are my 2 angles from the left equation. From the right equation, I get that cosine theta is equal to negative 1, and that only happens at one angle on the unit circle. It's 3 pi over 2. Nope, try again. It's pi. Yeah, I'm not very good with numbers. All right, cool. So theta could be any one of these 3 angles. 2 pi over 3, 4 pi over 3, or just simply pi. All right, I'm going to take a quick break from the problems to recall some information that we learned a few worksheets ago. So I'm going back to reference angles, which we talked about at length in worksheet 4. So if you check back to the notes on worksheet 4, you should see this exact picture show up. I believe it's in the first set of problems that are there on reference angles, where we looked at angles in each of quadrants 2, 3, and 4, and identified what the reference angle would be in each of those quadrants. Since the reference angle is always going to be that acute angle that connects wherever my angle is measured in standard position to the closest x-axis, so that in quadrant 2, it's that little red angle, and it's going to be the difference between pi and whatever angle I started with. In the third quadrant, again, marked in red, I have that reference angle. It's going to be the difference between my angle measured in standard position and pi. So I'll just take the difference between them. And then in that fourth quadrant, I need the difference between 2 pi and my angle measured in standard position. So I ended up with those 3 equations in red, and I'm going to solve each of those equations for the ones that show up in magenta there to the right of them. So if I wanted to get, if I knew my reference angle and had to get back to my angle in a specific quadrant, I could work with any of those 3 equations depending on which quadrant I'm in. So in the second quadrant, if I want an angle that's in the second quadrant, I want pi minus its reference angle. If I want an angle in the third quadrant, I'm looking at pi plus its reference angle. Fourth quadrant, 2 pi minus the reference angle. And then I also added in the equation for quadrant 1, although that one's pretty straightforward. If we're in the first quadrant, the angle and the reference angle are the same. So not a whole lot to really worry about there. So all of that is stuff that we talked about back in worksheet 4. Now we're going to add an element of inverse trigonometry to these reference angles. So say I know that cosine of theta is equal to x, sine of theta is equal to y, and tangent of theta is equal to z. I can actually use inverse trigonometry to find the reference angle in each of those cases, shown here below those, where in each case, that reference angle is just going to be the inverse trig function of my choosing. If it's cosine, I want inverse cosine. If it's sine, I want inverse sine. But the reference angle is always in the first quadrant, which means if I take the cosine inverse of a positive number, assuming that that positive number is less than or equal to 1, I'm going to get an angle that's in the first quadrant, meaning that the reference angle, regardless of which trig function I'm working with, is just going to be the inverse, whichever trig function, of the positive value, or the absolute value of whatever that function was equal to. So regardless of whether x is positive or negative, if I take the absolute value of x and then do the cosine inverse of that number, I'm going to get a reference angle. If I take the inverse sine of the absolute value of y, I will get the reference angle for sine theta equals y. Same thing with tangent. So anytime I'm looking for a reference angle and I need to use inverse trigonometry to get it, I just want to take the inverse whatever function of a positive number. So whatever that value is, just make it positive and then do the inverse trig function on it. So probably comes as no surprise that we're going to be putting that information to work in problems 6, 7, and 8. Our problems 1 through 5, all of my solutions came out to an answer that we have memorized from the unit circle. Questions 6, 7, and 8 will not come out to one of those 16 angles that we have memorized. Instead, we're going to need to use a bit of inverse trigonometry to solve for our answers. So take cosine theta equal to 0.74. So that's not one of the values that we have memorized from the unit circle, so we're going to need to turn to our inverse trig functions in order to get a solution. So starting with some of the stuff we've already been talking about, I know that cosine theta is greater than 0, right? Because it's equal to positive 0.74. So I want the quadrants where cosine is positive, which are 1 and 4. Cool. So we're just going to set those aside and go to get the reference angle. So that reference angle should be the cosine inverse of 0.74. And if we plug that into a calculator in radian mode this time, because we're working with radians, we're looking for solutions between 0 and 2 pi, I'll put it in radian mode and I end up with 0.7377 if I round to the 4th decimal place. So now to get my solutions that are between 0 and 2 pi, I just have to apply my reference angle to the 2 quadrants that I know I need to find solutions in. So in the first quadrant, my solution is just the reference angle, so theta is that 0.7377. Now in quadrant 4, I know that my angle there is going to be 2 pi minus the reference angle. So 2 pi minus 0.7377, and that comes out to 5.5455. Meaning that my solutions to that equation are those two angles, one in the first quadrant and one in the fourth quadrant. If we move on to problem 7, now we have sine of theta is equal to a negative 0.83. So now we're going to work with a negative value for whatever that sine number is. So this time I know that sine of theta is less than 0 because sine of theta is equal to a negative number, which means my solutions should be in quadrants 3 and 4. So that reference angle will be the inverse sine of positive 0.83. Because again, I want the absolute value of that number. So I'll take the sine inverse, positive 0.83, and I get 0.9791, again after rounding to 4 decimal places. And then I need to apply that reference angle to find solutions in the third quadrant and the fourth quadrant. In the third quadrant, I want pi plus the reference angle, which came out to 4.1207. And in the fourth quadrant, I want 2 pi minus the reference angle, which comes out to 5.3041, giving me those two solutions. And on to question 8. This time it'll be tangent. And I have the tangent is also going to be equal to a negative number. So tangent of theta is equal to negative 0.86. So tangent is less than 0, because again, tangent is equal to a negative number. And the quadrants where tangent comes out negative are quadrants 2 and quadrant 4. Quadrants 2 and 4. So that reference angle should be the tangent inverse of positive 0.86. Again, I always want to take, when I'm finding a reference angle, I always want to take the inverse trig of some positive number. And that comes out to 0.7103. If you try that on your own and say you get some number like 40 or 50 something, that probably means your calculator is in degrees. So just change it to radians, because again, we're working with radians in this worksheet. So now I need to apply that reference angle to quadrants 2 and 4. In quadrant 2, my angle is equal to pi minus the reference angle, which comes out to 2.4313. And in quadrant 4, it's 2 pi minus the reference angle, which comes out to 5.5729, giving me my two solutions for theta.